All right, so in the last problem we did, if you recall, we were trying to estimate the standard deviation of all men's heights, and we did it in a really poor way. What we did is we grabbed 3 men, we recorded their heights, and found the sample standard deviation. So we took these 3 men, we recorded their heights, we applied this formula, and we got a standard deviation of 1 inch. And again, what that number is describing is it's describing that the typical man is about 1 inch away from the mean. So this was a very small sample. It would be a very poor way to estimate the standard deviation of the height of all men. In other words, the population standard deviation. But it was, just an example. Okay, so why do we care about the standard deviation? Well, it turns out the standard deviation has all these really cool properties. So one of the properties of the standard deviation is as follows. So if a population's data has a normal distribution, then 68% of the data will lie within 1 standard deviation of the mean. 95% of the data will lie within 2 standard deviations of the mean. And 99.7% of the data will lie within 3 standard deviations of the mean. And I say draw a picture to describe the above statement. All right. Well, all right, let's look at some normally distributed data, or data that follows a bell shape. All right. So what I'm going to do is I'm going to draw this bell-shaped curve. Now what you have to do is you have to think of this curve that I just drew as, think of it as a histogram with really thin bars. So think of this as a histogram with really thin bars. So this histogram, the bars on my histogram are so incredibly thin you can't even tell where one bar starts and stops. Now, that's a bit of a lie. I mean, we're going to talk about what this curve means more in Chapter 6. But for now, that's how you can think about it. So if you were to say grab every man in the world and record his height, we'd expect men's heights to be normally distributed. So we'd expect a lot of men to be right around maybe 5'9", or about 69 inches. A whole bunch of men in that area, or in that range of data values. And then you would expect to have very few tall men and very few short men. All right, so normally distributed data, the mean would go right in the middle. So if we were looking at men's heights, the mean would be, population mean would be about 69 inches. So average height of men, all men, would be about 69 inches. All right, now let's analyze what this is saying up here. If data has a normal distribution, then 68% of the data will lie within 1 standard deviation of the mean. So what that means is if you go to the right by 1 standard deviation, in other words, you take the mean, you add on sigma, 1 standard deviation, and you go to the left 1 standard deviation, so you do the mean minus sigma, what you will find is that 68% of the data will be within these 2 numbers, these 2 heights. All right, if you move out another standard deviation, so you do the mean plus 2 standard deviations, and you were to do the mean minus 2 standard deviations, what you would find is that 95% of the data, so from here to here, 95% of the data would be contained between those 2 numbers. Now if you went out 3 standard deviations, mu plus 3 sigma, mu minus 3 sigma, you would find that almost all the data would be between those two heights, or those 2 values. So if you went between here all the way out to here, you would have 99.7% of data. So that's a cool property of the standard deviation if you're working with normal data. We're going to be working with normal data a lot. All right. Now the variance. The variance is the standard deviation squared. In other words, to get the variance, you take sigma and you square it. All right. Now, for right now, this is just a new number to us. We will use the variance in the future because it has certain nice statistical properties that the standard deviation doesn't have. So the variance is just the standard deviation squared. That's all we really know about it right now. That's all we really care about it. I'm just telling you it's going to be important later, in later chapters. So I say, what are the two formulas for the variance? Well, you got s squared for sample variance. Now, if you square the standard deviation, the square root symbol is just going to disappear. So you're going to have sum of x minus x bar squared, all divided by n minus 1. And for population variance, again, if you square the standard deviation, the square is just going to disappear. So you have the sum of x minus mu squared, all divided by n. So those are our two formulas for the variance.